Yeah, so hey everyone, this is Office Hours Week 6. We're looking at types of reactions, and right now we're looking at reaction 7, one of my favorite reactions from the assignment. You can watch this reaction. So if you didn't realize this, in Prep Activity 2, the list of reactions it gives you are the reactions from the lab. So you can actually go watch all of these reactions in the video that is posted to the Canvas page. At the bottom, there's a video I made of all the reactions. Actually, I think I forgot to do reaction number 8, but most of the reactions. So there's a couple things we want to think about for how we predict products. And Nick, I want to get to one thing in particular you mentioned, where you were talking about the AG2 idea. So we're starting with this, and we've got copper solid, right? So in this situation, the copper is not an ion, it's metallic, it's just pure copper. And we're mixing that with AgNO3. That's going to be aqueous, that's going to be an aqueous solution. And then when we do this reaction, you notice the reason I said it's not technically a metathesis is because metathesis is really a double displacement where you're trading one positive ion for another. And we don't have two positive ions. We've got a positive ion and a neutral ion. So this is actually a single displacement reaction. And when we do that single displacement, we're going to get CuNO3 to aqueous plus Ag solid. Now, the question is this silver ions? Is this silver solid? In the chemical reaction that if you go and watch the video for the chemical reaction, you can see actual crystals. You can actually watch silver crystals growing on the surface of that copper, which is part of what I think is really neat. When you do it in the classroom, some people refer to it as the Christmas tree reaction, because when it starts growing, it kind of starts at the top and then like fills out towards the bottom and has that kind of like pine tree look. And so the question becomes, well, what's the nature of this silver over here? Is it an ion that needs something to balance it? Or is it a solid? If it's just silver atoms. So you said you put silver 2, right? You said Ag2. Is that correct?
Yeah.
Yeah. So in this situation, what's the difference between, we've got an Ag with an Ag. What's the difference between those two silver atoms?
Not entirely sure.
Nothing. There's nothing that's different. So if we looked for the smallest ratio possible here, we would say, oh, it's just silver connected to silver. We're just going to call that Ag. Now, to get to the other thing you noticed, you said, earlier before I started recording, you said, the silver ions would need something to balance it. Now, the silver over here has a positive charge. What could we get that would balance that positive charge?
Either like oxygen or chlorine.
Why did you pick oxygen and chlorine?
Because I'm thinking an aqueous solution, it can dissolve in water.
Uh-huh.
So you could pull the oxygen from water and create hydrogen gas.
And why would you pull the oxygen, though? Because we're going to find a different way to do what you're talking about.
Or I know CuCl is a stable thing as well. So.
Yeah, but you know, so there's no chlorine here, so we can't do that one. But the thing you're looking for, and hopefully I'm not short-circuiting your thinking process, the reason you picked oxygen is because, or chlorine, those are both, what kind of ions are those?
Negative ion.
We want negative something. We want a negative something. Now, we could do it with a negative ion, or what's another negative thing that's going to exist in all of this?
I'm forgetting this.
What are atoms made out of?
Oh, electrons.
Electrons! So we could balance this charge by stealing electrons from the copper. And that's actually what's happening. So this silver is becoming stable with a 0 charge because we're stealing electrons from the copper. Notice the copper goes from a 0 charge to a +2 charge. So electrons are leaving the copper and going to the silver. And that will hopefully also give you a hint to the type of reaction we're looking at. When we see a change in charge,
Redox.
yeah. So when we see this change in charge, we're going to see that this is a redox reaction.
Okay.
Particularly, if we wanted to get more specific with our redox reaction, which we usually do, the thing that's gaining electrons is the thing that's reduced. The thing that is losing electrons is oxidized. Now, the part that always messes students up is you go from positive to 0 because you're gaining a negative charge. It's weird. You're adding a -1. But that's what's going on. You notice we also didn't charge balance this or balance this reaction properly yet. You were right to think that we need 2 silvers, but rather than subscripting to say that we've got some molecule, we're just going to say we need 2 silvers out front.
Okay.
And then we'll put a 2 here. Well, that doesn't look like a 2 at all. Whoops. There we go. So that's where we got 2 silvers, we got our 2 nitrates, and we've got our +1 and our +2, so now we're also charge balanced. So there's a lot to think about in there. For me, when I was learning types of reactions, I found the redox reactions were the most difficult for me to see. Precipitation reactions, I feel like, are pretty straightforward. You've got your solubility rules. You check your solubility rules, and you can tell whether solid forms or not. Straightforward. Acid-base reactions were also pretty straightforward. If I can remember my list of acids, I know that's got to be there, and water's probably a product. And then if it's not one of those, it's a redox reaction, and I start looking for that change in charge to explain it. The other thing that I want to point out, this was the other reason I really wanted to record this. Most of the time when we're asking about types of reactions, we're really focusing on the chemical type. So we've got our 3 chemical types. These are really looking at how the chemical compounds are changing. Your acid-base reaction, you're looking at that HOH situation. The precipitation, you're looking at the charges. You're looking at the cations and anions switching places. And the redox, you're looking at the electrons switch between materials. And then you've got what I call the arrangement type. And this is where you've got double displacement, also called metathesis. I hope I spelled that right. Single displacement. Synthesis. And decomposition. And essentially, all of the chemical reactions we're looking at can have a chemical type and an arrangement type. So you can have one of each. another thing I wanted to mention to you, Nick, the idea that the silver would pull apart the water to get oxygen out is not an entire, is something that's a reasonable thought to have. It's not what happens in this case, but it's something that's reasonable to think about, and it really comes down to, well, how much energy does it take to rip water apart versus how much energy does silver get by gaining that electron? And that is starting to get into the idea of reduction potentials in terms of how much energy it takes for these things to happen. The reason that silver can rip copper apart is because of the energy comparison of silver +1 to copper +2 and how well silver can attract electrons to it. That really starts to put, if we wanted to get really numerical with that, that would get us into Chem 125, 128, where we actually look at electrochemistry and standard reduction potentials. And you can do these kind of energy comparisons of like, which things could silver rip apart versus which things can't it rip apart to get those electrons, to get that negative charge to it.
Awesome, thank you.
Hey, you bet. Going on to number 6, or back to number 6 rather. Oh, I don't want to erase that. I'm going to leave that. So I like to think about it in terms of, we've really got 2 ways we could think about our reactions types. So we're looking at reaction number 6 now. We've got our chemical type and our arrangement type. So this says a 2 centimeter piece of magnesium ribbon is ignited in a Bunsen burner flame. So here's what we know. We've got a piece of magnesium metal is ignited in a Bunsen burner flame. Do I put fire as the other reactant? What is the magnesium actually going to react with?
The oxygen?
Yeah. It's going to react with oxygen gas. Right? And it turns out it could have reacted with the nitrogen gas or the helium or the argon gas. There's different things that are the carbon dioxide gas or the water gas that's all just kind of in the atmosphere. But because of if we looked at the reactivity of all of those things based off of their electronegativities, their electron clouds, their hybridizations, we'd see that oxygen is the most reactive gas that it could be interacting with. So we say, okay, magnesium reacting with oxygen. I've got to figure out how I'm going to do this rearrangement now. Now, obviously, this isn't really, we can't do a double displacement because this doesn't have something to displace. So when we do this, it doesn't really look like a single displacement either because this is O2, this is Mg. And so I'm just going down my list of arrangement types, because that's just how we rearrange the elements in the reaction rather than what's chemically happening. Now, a decomposition is when you go from one thing to 2 products. And we've got 2 things, so it's not a decomposition. So I'm going to guess that this is a synthesis reaction where we've got 2 things going to 1 product. So I'm going to go ahead and make this magnesium oxide. Now, before I get too far ahead of myself, I want to make sure I'm making a good compound. So should it be MgO2? Should it be Mg2O? Should it be Mg3O2? Like, what's the proper ratio of charges in order to make this a good compound? For that, we need to know that from the periodic table, the common charge of oxygen is?
-2.
-2. The common charge on magnesium is?
+2.
+2. Plus 2 minus 2, that's going to give us a neutral compound. So actually, just MgO is already the balanced compound, the charge-balanced material. And then I can go ahead and I can balance the chemical reaction. I'm going to need a 2 here to get my 2 oxygens, and then a 2 here to get my 2 magnesiums. So I've got it mass balanced, I've got it charge balanced. It's not on the solubility rules, but if we looked at the solubility rules, oxides, if we looked it up, oxide compounds are typically solids. Also, there's no liquids here, so it would be weird if it went aqueous, like where'd the water come from to make it aqueous. So this is our chemical reaction. Let's see, what's it asking us to do? We've got our predicted product. We've got our reactants. We've got our product. And now we have to figure out our type of reaction. So it's not no reaction, that's for sure, because a reaction definitely happened. And have you seen magnesium burning before? If not,
I don't believe so, no.
Oh, okay. Hold on. I gotta find this video. If you haven't watched the chemical reaction videos, I had a lot of fun making these videos.
Did you burn magnesium in them?
I did, so I'm finding that video right now. So if you check this out, this is with the timestamp. Those of you watching, go find it. It's at 339 seconds in my types of reactions video, or 5 minutes and 39 seconds. You can watch magnesium metal burn. Magnesium is really interesting in the way it burns. It burns incredibly hot, and once it starts burning, it can actually burn underwater. It produces enough heat that essentially creates a boiling area of water around it and can keep burning, just with the oxygen that's dissolved in water. It also burns hot enough that if you had a small container of magnesium shavings on top of a car, and you can find videos of people doing this to like old junkers and stuff like that, just as like, you know, the pop science things, but you light it and it produces enough heat that it will actually burn through the metal, through the engine block, and melt a hole straight through the car. Old motors, this used to be a huge problem. I think it was motors in the mid-60s, or maybe it was the mid-70s actually. They started trying to make cars more lightweight, and they started using some magnesium components and some magnesium alloys in their engine components. And if they caught on fire, it was really bad because magnesium burns a lot. Let's go ahead with that brief kind of, like, we're just at my favorite part in the quarter where we actually start to get to do chemical reactions. And there are a lot of really neat chemical reactions. Let's go ahead and figure out the chemical type. Now, a solid is formed. So some people jump to the idea that this is precipitation, but precipitation is a solid being formed from 2 liquids. And we don't have any liquids. Acid-base reaction, oxygen can act like a base, but we don't have anything to really act like an acid. So probably not acid-base. This leads us to think that it could be a redox reaction. There's another really good hint that it's a redox reaction. If you remember, redox stands for reduction, oxidation. Oxidation means adds oxygen to something. This reaction is adding oxygen to magnesium. So it is like kind of the definitive oxidation reduction reaction. Another really great example of a stereotypical redox reaction . Balancing. 2, 3, 6. Oh, not 6. Math is hard. 4. I got my 6 oxygen, 6 oxygen, 4 iron, 4 iron. Iron reacting with oxygen to form iron oxide, which we also call rust, right? Metal rusting is a redox reaction. This actually also happens to pretty much all metals that are left out in an environment that has oxygen. Now, the violence of that reaction, how much it happens, the energy released, how fast it happens, those are not here. Actually, if you leave a piece of magnesium metal just sitting out in the air, it will slowly start to turn a crusty white. And that's from magnesium oxide just slowly forming. But if you give it a little energetic kick by lighting it on fire, you get the reaction to speed up dramatically, and you get this huge flare, essentially. Iron oxide is kind of the same thing. It happens really slowly, and it's just rusting, but it's actually the same type of idea of a reduction-oxidation reaction. Oxidation, adding oxygen to something. Iron is going to lose electrons, oxygen is going to gain electrons. Reduction-oxidation reaction. One more side note before I stop recording. The military uses magnesium flares during night combat. And if you've ever seen a magnesium flare go off at night, it's pretty incredible. And there's probably videos of that someplace on the internet. So we're going to do a quick problem from the practice problems. We're looking at the reaction. This is probably about a third of the way down. We've got this reaction of 2HClO4 plus magnesium. This is aqueous solid, goes to H2 gas. I didn't give myself enough space, so I'll just write it right next to it. MgClO4 aqueous. So in order to kind of make sense of what's going on here, we want to name all the compounds, we want to name the products, and we want to figure out what type of reaction it is. So this is perchloric acid with magnesium metal to form hydrogen gas and magnesium perchlorate. The thing, in order to really make sense of this in terms of the redox reaction that you were asking about, is we need to first identify the common charges on everything. Hydrogen's a +1 charge. The perchlorate anion is a -1 charge. Magnesium is a 0 charge. Notice the perchlorate anion actually doesn't change at all from the reactant side to the product side. So this whole perchlorate anion thing over here, and I put parentheses and I forgot to balance the charges. This perchlorate anion is a -1. Magnesium's common charge when we form a magnesium ion is +2. So in order to have a charge-balanced compound, I need a subscript 2 there. That's also why we've got the 2 there. And we can see now just the fact that magnesium is going from 0 to +2. 0 to +2 means that it's losing negative charges. It's becoming more positive. So that is the thing that is oxidized. That's the thing going through oxidation. The thing that is going to be changing charge in the other way is this hydrogen going from a +1 to a 0, right? Whenever we've got our diatomic gases, there is 0 charge. So I'm losing a positive charge, or rather I am gaining a negative charge. Part of what really messes students up with this is just the idea of gaining negatives, right? We're gaining negatives or we're losing negatives. So we're becoming more positive, and that's the kind of like flipping it both directions in our head.